Hello everyone, we are Team 21041, Methods for Estimating Hydraulic Hose Sag. I am Rebecca Garcia.
I am Mohammed Al-Khalaf.
I am Farah Lloyd.
I am Ross Felton.
I am Josiah Wagner.
I am Matthew Jakubowski, and I am the team lead for this project.
Our sponsor is Caterpillar, but more precisely, the hydraulic hoses on the large mining equipment portion of Caterpillar. The purpose behind our project is to create an estimating system of where the hoses will hang when they are installed on the mining trucks. This is important because when the Caterpillar designs their equipment, there tends to be a lot of moving parts, and where these hoses hang could be in a mechanical device and therefore ruin the hose and cause failure across the equipment. To combat this, my team has put together an Excel document applying an equation that is commonly used for power lines to predict the sag of the user-given characteristics of a hose. To test the accuracy of this Excel document, we also built a test structure, as you can see behind me, with a hydraulic hose will be mounted inside of it and displays the amount of hose sag. This structure is adaptable to a variety of hose diameters and has the future capability of testing any length of hose.
The following is an overview of our system requirements. For our application, we have our application accuracy, which needs to be plus or minus 5 centimeters. The user also needs to be able to select the hose model and input the length, span, and diameter. As for our testing center, our hoister needs to be capable of testing the hoses contained in this table, and it should have the capability of measuring the hose end accuracy.
Next, we have the system block diagram. We divided the system block diagram into two systems, the test center on the left and the computer on the right. So on the test center, we have the hydraulic hose mounted in the middle. That's the long horizontal box in the middle. Each end of the hose has a hydraulic hose going from the pump and the fluid reservoir. And then we have optical sensors laid along the hose. These feed into a microcontroller board, which then feeds into the digital display. Then the computer, we have a user input of the hose characteristics, fluid characteristics, into the Excel document. This will then output the displacement to the user.
Here we have our trade study. For our trade study, we focused on the frame, the sensors, and the application. For the frame, we considered a horizontal and 90-degree. For the sensors, we considered an ultrasonic, a resistor type, and an optical sensor. And for application, we considered either MATLAB or Excel. For our frame, we decided on a horizontal since this would allow us to build it in sections and would also allow for additional sections to be added in order to increase the size of the frame. For the sensor, we went with an optical sensor since this would provide us the accuracy with needed at a reasonable price. For our application, we decided to go with Excel since it is the most user-friendly and is readily available.
This is the Caterpillar hose sag calculator. This is the instructions page, which will show the user how to apply the actual calculator. Prior to us going to the results page, we're going to go to the last page, which is our data page. This page actually has all of the calculations based off of the 3 different types of hoses and their subtypes. When the user enters it in using the calculator, these will automatically change and then therefore change all of the following calculations that are pre-done in this section. This is the results page, which has their entering information and the outputs. So using the actual button, we can see there are 3 different types of hoses that can be chosen from, along with multiple diameters. A message box pop up telling the user which hose and which diameter they chose. In the inside parts where you actually have to enter the information, the user will be able to choose the length in question. And you can see over here to the left that this actually represents what the user entered and the individual outputs based off of those. The next section is going to be the actual code of the VBA. From here, you can see this is the basic buildup of how to incorporate the different buttons. Caterpillar will be allowed to enter in more buttons and incorporate new hoses.
Okay, here is our sensor suite for measuring hose sag. On the left here, we have our Arduino Do 32-bit microcontroller. And then on the left here, we have our optical sensors, 1, 2, and 3. These are the Adafruit VL53L0X time of flight sensors. Off of our SPI header over here, we have our display driver board. This is the Adafruit RA8875. which drives our 7-inch 800 by 480 resolution touchscreen display. On the display, you can see the on-off button, which if we hit that, starts recording values. Pressing off stops the recording. Hitting reset clears the values. And then the start and stop buttons control the timer down here.
We then use this point design to create our initial SolidWorks model. Then our analysis showed that the temperature would not have as great of an effect on the sag as we initially predicted, and thus we went ahead and removed the enclosure that was in the initial design as well as the refrigerator unit and temperature sensors, and went ahead and designed our second SolidWorks model, which we can see here. Upon getting some input from our mentor and further analyzing our frame, we went ahead and made a few more changes and ended up with this drawing, which is our final design.
The fabrication process was not difficult to complete. It merely consisted of cutting out a lot of the small pieces, which could have been done easy with an angle grinder or a drill, and then everything else would be able to be ordered to size.
We began by connecting our vertical structures to our galvanized steel tubes using our L-brace and T-brace brackets and securing everything with nuts and bolts. Once all the vertical structures were attached, we went ahead and moved on to adding our mounting brackets to each end of our structure. This would allow us to attach our hoses. Then we added our galvanized steel tubes to the top of our frame, and we went ahead and moved on to our fluid reservoir and pump assembly. We began by attaching our fluid reservoir to the pump and used our hydraulic hoses here to attach those to our frame. We then attached the hydraulic hose we would be using for testing, and here we have an image of what the full assembly looks like.
The analysis showed that the initial predicted sag from the application was outside of the accepted margins, and therefore adding a correction coefficient that matches to each individual hose then brought the application's predicted sag within the bounds of accepted margin. This is also for the hoses that do not have oil or fluid flow.
All of our requirements were met. The application accuracy was met after introducing a correction coefficient to the initial equation. The user can select and input the user properties. Also, the test center can test all the hoses provided, and the measurement sensor met our accuracy requirements.
Learn that just because something theoretically fit in the drawing doesn't mean it would easily fit the way during assembly. A setback we had was that some of the parts did not have dimensions only, which made planning more difficult since we had to wait for the parts to arrive. Special thanks to our mentor Eddie Baba for guiding us through this project. Thank you to the senior design staff for making this experience possible and making us better engineers.